Hello, hello. Am I live? Hello. Yes. The audio is good. Video is streaming. Okay, let's go. I'm just setting up video. Okay. Mhm. Okay. Okay. As the title suggests, I will be learning segment trees and Fenwick trees today because it has been asked in Q4 of weekly and now bi-weekly contest of late code, and I was not able to solve those questions. So we'll be learning that hopefully if we ever get that type of questions, we'll be able to solve those questions in the future. But first I need to learn those techniques, those advanced techniques. But first, before starting that, let's first solve our late code's daily problems first. Then we'll move on to learning segmentaries. I will be sharing my screen now. Hopefully it's working. Yeah. Okay. Let's see. What do we have for today's problem? Count odd numbers in an interval range. Okay. This is an easy problem. Given oh, given two non-negative integers, low and high, return the count of odd numbers between low and high inclusive. Low is 3, high is 7. Output 3 because we the odd numbers are 3, 5, and 7. Hmm. 8, okay, 8 and 10, we only have one number which is 9. Oh, the constraints are pretty high, so we cannot do O of n solution as well. It needs to be something better than that. Yeah. This question is actually easy. Let's see. Okay, I should write the comments here. Um, yeah. We have low and high. We need to find number of odd numbers. So in range between 3 and 7, we have numbers 3, comma 4, comma 5, comma 6, comma 7. Okay, what does this mean? We have the number of odd numbers are 3, 5, and 7. So an easy way of solving this is to just calculate the range, right? Interval range, that is 7 minus 3, which is equal to 4 divided by 2. Why divided by 2? Because we'll get the basically get the bucket size from 3 to 7. and then we can count, there will be only even or odd numbers in it, right? So equal number of even and equal number of odd numbers within that range. So just divide it by 2, and this is equal to 2. And we need to add plus 1, because when we subtract 7 minus 3, it will give us the range from these numbers, right? We'll get these 4 numbers. So, we need to add plus 1 here, which will give us 3. But this is a pretty easy question. We can solve this in of one solution. But what if this is even, the numbers are even? What if the numbers are even? What do we do now? Just okay, so if the numbers are even, if low is even, increment by 1. If, and same goes for high, but instead of an increment, we decrement it by 1, because we need to stay in the range. If low, okay, and 1 is equal to 0, which is even, just increment low by 1. If high is even, decrement high by 1. Now just return high minus low. Divide by 2 plus 1. This should work. Yeah, this was a pretty easy question. So push. Okay. I also want to add, like yesterday's uh weekly contest, bi-weekly contest solutions, as well as today's weekly contest solution. I guess they have not created the problem, but I guess, oh, bi-weekly contest. Yeah, they have. Great. One, they, one, push. 3766. Okay, next, the question, and then the third problem. Click add the command. Command. I want to press command plus space, but I accidentally keep pressing command plus V. Wait, okay. Now, this was the question which required Fenwick tree or segment trees, basically, but I was not able to solve it yesterday. Let's check the solution if anyone has solved it. Have we created the numbers that they have? Wait, let me just first search the problem number on YouTube. Let's check. Mhm. Okay, let's save this as well. Wait, and wait for a minute. Check it. So perfect. Wait, push. Start. I was able to solve only two problems from today's big looking test. Because third problem, the part on which the problem was difficult, was difficult. And it commit. Perfect. This question, I attempted this question. I was able to solve it using of n square solution, but the constraints were pretty high. It was 10 power 4. No, sorry, 10 power 5. So 10 pass, uh, I got it clearly. So yeah, it's, I will solve this question eventually. But let's first solve this problem. Should close this, right? Don't need it.
Welcome back to the channel. So today we'll discuss all four problems asked in today's lead code biweekly contest 171. Let's look at the first problem. You are given an integer num and the number num is called complete prime number if every prefix and every suffix of num is a prime number, right? So we have to return true if the number is a complete prime number. The prefix we have to the number is prime or not true. X is equals to true or not. Now if the number are odd, what we can do, we can easily use a for loop from I equals to 3, I into I less than or equals to x, I plus equals to 2, right? So this is the standard algorithm, right? So here the complexity is order of square root of n, square root of x. and just check if any of the number divides this number x. If any of the number divides, just return false, that is not a prime number, otherwise return true. So this function just check if the number is prime or not, and apart from it, the code is easy. Just go through all possible prefixes, like generate all possible prefixes, and just check if the number is not prime. If the number is not prime, right, if the current prefix is not prime, just return false, because the number would be complete prime number if every prefix
If you got the prefix like that, yeah. Hmm. Also convert your link into a string. Makes
and every
sense.
return false. And similarly, as soon as you get any non-prime suffix, return false. So third problem, actually this problem would be x minus 1 will go to x plus 1. Like, so if neither x minus 1 nor x plus 1 is a binary representation, like binary palindrome, just go to x minus 2.
Hmm.
Then it will check x minus 2, then x
This
plus
is
2.
the same thing
If
like the
neither
whole
of
time.
third problem, actually this problem is pretty easy. I mean, I found it, this third problem is much easier than first and second. Even you also would think the same by looking at the problem. So here it says you are given two integer array, technique 1 and technique 2, each of length n, where n represents the number of tasks to complete, right? So if the ith task is completed using technique 1, so if you complete the ith task using first technique, you earn technique 1 I point. And if you complete the ith task using technique 2, then you earn technique 2 points, right? You are also given an integer k that represents the minimum number of tasks that must be completed.
Wait, okay. हो. Continue. हाँ, हाँ.
Completed using technique 1, right? So k is the integer. I mean, so you have to complete at least k number of tasks by using technique 1. So you must complete at least k tasks using technique 1 if they don't need to be the first. Okay, so they didn't, like, they don't have to be the first k technique 1. It could be any random, right? So out of all this technique 1, just like you must choose at least k tasks to complete using technique 1, and the remaining can be completed either using technique 1 or technique 2. It doesn't matter, it's up to you. So we have to find out the integer that denotes the maximum total point that you can earn, right? Yeah, let's see how we can approach it. So in second problem, we are given two arrays, right? Technique 1, technique 2. And so let's say there are n number of total tasks that you have to complete, and out of them, at least k must be completed using technique 1, right? And we have to find out what is the maximum points that you can earn, right? So we will do it in two steps. First step, let's assume you have completed all the tasks using technique. So currently your total points earn is nothing. So in count the point, maximize your task, at least k number of task has to be completed using technique 1. So you must choose the first k task because those are having the maximum gains, right? So just add these k numbers, and afterwards for these numbers, right, remaining n minus k, this is up to you. Let's say the gain is positive, then isn't it better to complete this task using technique 1? Like, if the gain is positive, then it's 1.
Hmm.
So I complete that. Here is the code. This code is exactly how I have explained k task. Just check if your gain is positive. If your gain is positive, this is the fourth problem. So yeah, here is the fourth problem asked in today's contest. So it says you are given an integer array nums of length n and integer k. Now we know what is inversion. Inversion is the pair of indices I and j such that your I is less than j, but the value is more than nums
Greater
of
than.
j, right?
Hmm.
Nums of I is more than nums of j. This is the standard inversion definition. Now the inversion count of a subarray is the number of inversion within it, right? We have to find out the minimum inversion count among all subarray of size k. So, yes, yeah. So you have to go through all possible subarrays of size k and just find out its inversion, and and among all those inversion of k length subarray, just print the minimum possible inversion, right? So yeah, that's all about the fourth problem. Now let's see how we can approach it. It's really good problem, right? It uses Fenwick tree. I have solved using Fenwick tree. Yeah, let's see how we can approach it. In fourth problem, if you notice, your length is only up to 10 to the power 5, but your numbers are up to 10 to the power 9, right?
Yes.
So we cannot apply directly, like we cannot create an array of size 10 to the power 9 or something, right? So what we will do something smart. Let's say your number, we know that the nums, like the unique numbers can be only up to 10 to the power 5, right? That is for sure. Though your number is up to 10 to the power 9, but the total unique numbers are only up to 10 to the power 5. So what we will do, we will convert into a compressed array. Maybe it sounds a fancy words, but it's very simple. Let's say your given array was something 3, 5, not 3, 5. Let's say your given number was something 10, 12, 11, 14, and let's say 9, for example, right? Let's say this was your original array, right? But what I'll be doing, first I will convert, like I will sort them number, right? These numbers are 9.
Okay.
Like if you sort them 9, 10, 11, 12, and 14, right? So for corresponding 9, what I'll be
Wait, I cannot see part of the adjustment.
doing, I will now treat 9 as 1, I will treat 10 as 2, I will treat 11 as 3, 12 as 4, and 14 as 5. Now we will kind of do a reverse mapping. If you do a reverse mapping, then your 10 was what? 2.
2.
Now this 10 is 2, 12 was 4, 11 was 3, 14 was 5, and 9 was 1, right? So now what I'll be doing, this was your original given array. Now I will convert this array to this array, because to calculate inversion, it doesn't matter what is your number. It just matter if your I is less than j, a of I is greater than j, a of j or not. That's it. It doesn't care about what is your current number, right? It just care about this condition. And if you notice it here, this condition will exactly be satisfied in this array also. See, 10 is less than 14 and 12, right? See, 2 is less than corresponding 4 and 5.
Yeah. Yes, this makes sense.
And similarly, 10 is more than 9. See, 2 is more than 1. So this array is exactly same in terms of finding the inversion. Because so why I am doing is that if you convert this array into this normalized array, we can easily apply an standard algorithm such as segment tree or Fenwick tree. Because in those situations, you have to create an array of these numbers, right? Whatever that max number is. So whenever you see a problem where you have to create a size that, like, the size is up to the max number, but the max number is up to 10.9. So just think about it. If you convert this array into its normalized array, this is like some people also call it normalized array. It's possible or not, like the integrity of the problem shouldn't change, right? Here if you see, if you convert this to a normalized array, your integrity of the problem is not changing, it's exactly the same. So it's better to use that. So that's what I'll be doing. I'll be converting this original array into this normalized array. This is pretty easy. Just keep all the unique numbers, sort them, find the indices, and just convert this into this array, right? After that in this problem, we have to find out the minimum inversion among all k array k size subarrays, right? For each k size subarray, we have to find out the inversion, and among all those k inversions, just find out the minimum, right? So here what I'll be doing, let's assume this is your k size subarray, right? And I want to slide it. So I'll be using some sliding window kind of mechanism, right? For each k window subarray, right? I'll be kind of sliding it right side by 1. So if you so let's say for this k size subarray, the size of this subarray is k. The size of this subarray is k. Let's say for this k size subarray, I have already calculated the inversion value, right? Let's say that inversion is something inversion, right? I already have inversion calculated for this k size subarray. Now let's say I slide this subarray by 1. So now you have to include this number and you have to exclude this number, right? So this number should be removed, not this number, the last number here. let me, yeah, this number should be removed and this number should be added, right? So let's see how is your inversion affected using these for these two numbers. See, for these numbers your inversion is not going to change, right? For the sub array this, your inversion is not going to change, right? So the only thing that matters is what are the values of these two numbers, right? So this included number and this excluded number, right? So let's first handle this excluded number, right? So we know that for this array, right, for this array of size k, the inversion using this was contributed in this inv, right, this in this inversion value. And what would be those inversion? That inversion would be what are the numbers, I mean the count of number in from the next element onwards, right, in this array. Like the inversion, like the contribution of inversion by this number would be how many numbers are there in this range whose value is less than that x, right? Because you know that for the inversion these two conditions should be satisfied. The first condition is already satisfied, like the index of that number is anyway less than all these numbers, and the value should be more than these numbers, right? So just check how many numbers are there whose value is less than this number, right? Less than this number. So that we can calculate using Fenwick tree. So in Fenwick tree we would be storing in numbers are there whose value and the value should be more than these numbers, right? Satisfied. Like then you know that for the inversion these two conditions should be satisfied. The first condition is already satisfied, like the index of that number is anyway less than all these numbers, and the value should be more than these numbers, right? So just check how many numbers are there whose value is less than this number, right? Less than this number. So that we can calculate using Fenwick tree. So in a Fenwick tree we would be storing information based on this array, right? Based on this array, because we know that this array exactly the same in terms of finding inversions. So I would highly recommend to learn Fenwick tree. I mean, what is Fenwick tree, how it works, because in this problem I'll be directly applying how Fenwick tree is used in this problem, right? I won't be able to explain in this video only. So maybe if you need, I can create a separate video for Fenwick tree in a detailed manner. So yeah, here what we will do, we will first remove it, like remove that number and just check how many numbers are there which is less than b. So that inversion minus equals to whatever that value is. Let's say that value is k1, right? Now for this number, right, so that is done. This part is done. We have handled this excluded number. Now since that number is already removed, now your subarray is, like the size of the subarray is k minus 1, right? Now you want to include this number, right? So to include this number, now let's see how your inversion is affected by this number. So we know that for inversion these two conditions should be satisfied. So the first condition is already satisfied. The index of that number is more than these numbers. Now to let the inversion count increment, your current number has to be smaller than these numbers, right? So your contribution would be, like the inversion for this number would be how many numbers are there whose value is more than x, right? For the excluded number we had calculated how many numbers are there which is less than this number, but for the added number we have to calculate how many numbers are there whose value is more than this number, right? This added number, let's say that number was x. How many numbers are there whose value is more than x? Let's say that count is k2. So your inversion would be incremented by that k2, and that's it. This is your current, like this is the inversion value of this slided, I mean, so like once you slide this window by 1, now your inversion would be calculated based on this these values, right? So just find the minimum inversion among all those subarrays of size k. So yeah, I hope you understand. So this is the approach. Now to calculate, right, since here we have to kind of update and query, right? So once you remove it, your updation value should be -1, like your contribution should be -1. -1 means you have removed it, and if you want to add the number, your contribution would be +1, right? +1 and -1. By -1 if you remove the number, and plus
एक बार मेरे एक दोस्त को पूछा गया था। बाइनरी इंडेक्स ट्रीज एक ऐसा टॉपिक है जो इतना डिफिकल्ट नहीं है, एंड अगर आप इसको एक बार समझ लोगे ना तो इसका कोड बहुत छोटा होता है, एंड इंटरव्यू के कोडिंग राउंड्स में आप फटाफट लिख सकते हो। सेगमेंट ट्रीज के काफी सारे क्वेश्चन हैं जो बाइनरी इंडेक्स ट्रीज से हो सकते हैं, एंड इसलिए इसका काफी फायदा है क्योंकि सेगमेंट ट्रीज का कोड बहुत लंबा होता है एंड बाइनरी इंडेक्स ट्रीज का कोड काफी छोटा है। तो हम देखते हैं कि यार यूज केस क्या है, बाइनरी इंडेक्स ट्रीज किन क्वेश्चंस में यूज होता है। तो लेट्स सपोज अगर हमें एरे दिया गया ए, ठीक है, एरे का साइज है n और n है लेस देन 10^5। अब इस एरे पे मेरे को दो टाइप की क्वेरीज करनी है, एंड जो नंबर ऑफ क्वेरीज है वो भी 10^5 है। अब क्वेरी क्या है, दो टाइप की क्वेरी। पहली टाइप की क्वेरी क्या है, मेरे को एक आई इंडेक्स दिया है और मेरे को a of i इज इक्वल टू x करना है, रिप्लेस करनी है किसी वैल्यू को। दूसरी टाइप की क्वेरी है, मेरे को l to r का सम चाहिए एरे में। अगर आप नेइव मेथड से इसको सॉल्व करने की कोशिश करोगे तो ये आपको टीएलई एरर दे देगा, नॉर्मल कोड। तो ये जनरली सेगमेंट ट्री से सवाल होता है, बट बाइनरी इंडेक्स ट्री से हम काफी छोटे में कर सकते हैं। तो ऐसे क्वेश्चंस के लिए हमें बाइनरी इंडेक्स ट्री चाहिए रहता है। तो देखते हैं कि बाइनरी इंडेक्स ट्री होता कैसे। तो बाइनरी इंडेक्स ट्री सीखने से पहले हमें एक बिट मैनिपुलेशन की छोटी सी टेक्निक सीखनी पड़ेगी। वो टेक्निक क्या है कि अगर हमें एक नंबर दिया गया है x, अब इस x की बाइनरी रिप्रेजेंटेशन है, मेरे को राइट मोस्ट बिट फाइंड करनी है जो सेट है। बेसिकली लेट्स से इस कोई राइट मोस्ट सेट बिट फाइंड करनी है, यानी कि ये बिट की पोजीशन फाइंड करनी है, ठीक है। तो इसकी एक बिट से बहुत सिंपल सी टेक्निक होती है, हम वो टेक्निक देखते हैं। लेट्स से x इज इक्वल टू 1 जो है राइट मोस्ट सेट बिट है एंड b सारे 0 है, ठीक है। b सारे 0 है क्योंकि अगर ये राइट मोस्ट सेट बिट होगी तो b ऑब्वियसली सारे 0 होंगे। तो किसी भी बाइनरी नंबर को मैं ऐसे रिप्रेजेंट कर सकता हूं a1 b की फॉर्म में, जिसमें a कोई भी एक रैंडम नंबर है, बाइनरी नंबर 1 राइट मोस्ट सेट बिट है और b सारे 0 है। अब अगर मैं निकालूं -x किसके बराबर होगा? कॉम्प्लीमेंट x कॉम्प्लीमेंट प्लस 1 के बराबर है। अब इसमें अगर x की वैल्यू सब्स्टिट्यूट करें, a का कॉम्प्लीमेंट में चला जाएगा जो है ये 0 1, तो ये किसके बराबर होगा? x है, ये है, तो इससे डाल दी ऐसे। तो यार अब आते हैं बाइनरी इंडेक्स ट्रीज पे। तो बाइनरी इंडेक्स ट्रीज के लिए सपोज हमें गिवन है एक ए एरे गिवन है जिसका साइज है n। अब एक बीआईटी एरे मान लेते हैं जिसमें लेट्स से जो i है वो एरे का एक इंडेक्स है। लेट्स सपोज
Hello friends, my name is Tushar and today I'm going to talk about Fenwick tree or binary index tree. Before going into the details of what Fenwick tree is, let's look at the use case which Fenwick tree is trying to solve. So Fenwick tree is used to get prefix sum of an array. For example, if I'm given an array of 7 elements from 0 to 6, so Fenwick tree will help me answer queries like what is the sum from 0 to 4? So the sum from 0 to 4 is 3 plus 2 5, 5 plus 6 11, 11 plus 5 16. What is the sum from 0 to 6? So the sum from 0 to 6 is 16 minus 1, 15 plus 2, 17. So queries like this is why I use Fenwick tree. What are the other alternate solutions if we did not use Fenwick tree? One solution is to keep a prefix sum based array. So for 0, it's the 2 is 5. So if an array is large and if there are many updates in an array, this prefix sum based array doesn't scale very well. Another possible alternate is to use segment tree. If you don't know what segment tree is, I have another video going over the details of segment tree and you can watch that video. The problem with segment tree is it's slightly more complicated. It takes in worst case 4 of n space to store segment tree for n array, n elements in an array, and in worst case it takes n space to store segment tree for n array, n elements in an array, and in worst case it takes 4 of log n time to search into to do a range sum query in a segment tree for an array of size length n. So this is where Fenwick tree comes into the picture. The space it takes to store Fenwick tree is O of n.
Just a moment. Change place. Okay. Okay, I am back.
The amount of time it takes to search into Fenwick tree is O of log n. The amount of time it takes to update every element in Fenwick tree is O of log n, and the amount of time it takes to create a Fenwick tree for the first time is n log n. Next, let's look at the implementation details of Fenwick tree. So now I'm going to create a Fenwick tree based on a given array. So I'm given an array of 11 elements starting from index to 10, starting from index 0 to 10. So my Fenwick tree will go from index 0 to 11, one more node than the actual array. So let's see how I built this tree right here. So this is a conceptual tree. My actual tree will be stored in a form of array, but this is easier to understand, which is why I have it this way. So 0 is a dummy node and doesn't store any information, and rest of the nodes 1 to 11 will store the prefix sum. Why I have the tree this way? Let's look at it. Why 0 is parent of 2? If you look at the binary representation of 2, that's 1 0, and if you flip the rightmost set bit, it becomes 0 0, which is 0, which is why 0 is parent of 2. If you look at binary representation of 8, that's 1 0 0 0. If you flip the rightmost set bit, it becomes 0 0 0 0, which is again 0, which is why 8 parent is also 0. If you look at 10, binary representation of 10 is 1 0 1 0. If you flip the rightmost set bit, it becomes 1 0 0 0. And this is 8, which is why 10's parent is 8. Let's look at 11, 1 0 1 1. If you flip the rightmost set bit, it becomes 1 0 1 0. This is 10, which is why 11's parent is 10. So hopefully it is clear why our tree looks like this. To get the parent, all you have to do is get the binary representation, flip the rightmost set bit, and then it gets a parent. Later on, we will look at how you can efficiently flip the rightmost set bit. Now let's try to fill up this tree here with the prefix sum information.
Okay.
One thing to notice is that every number can be represented as a sum of power of 2's. For example, 10 is 2 raised to 3 plus 2 raised to 1. 11 is 2 raised to 3 plus 2 raised to 1 plus 2 raised to 0. 5 is to store the prefix sum. Let's see how this works. As I said, 0 is a dummy node, so the only information it has in its node is 0. Let's start with 1. 1 can be represented as 0 plus 2 raised to 0. So what I'm saying is, in my original array, starting from index 0, the sum of next one element will be stored at 1, so 3. And I'm indicating that the range sum of range 0, 0 is stored at 1. Let's look at
What?
0, the sum of 2 raised to 0. So what I'm saying is, in my original array, starting from index 0, the sum of next one element will be stored at 1, so 3.
Hmm.
And I'm indicating that the range sum of range 0, 0 is stored at 1. Let's look at 2. 2 can be represented as 0 plus 2 raised to 1. So again, starting from 0, the sum of next two elements will be stored at 2. So 3 plus 2 is 5, and this is 0, 1. Let's look at 3. So in my original array, starting from index 2, the sum of next one element will be stored at 3. So that's minus 1, and this is 1. This is 2, 2,
What?
minus 1. Let's look at 3. So in my original array, starting from index 2, the sum of next one
The sum of next one element.
element will be stored at 3. So that's minus 1, and this is 1. This is 2, 2. 4. 4 is 0 plus 2 raised to 2. So starting
0 plus 2 raised to
from 0, the sum of next four elements will be stored at 4. So 3 plus 2 is 5. 5 minus 1 of next four elements will be stored at 4. So 3 plus 2 is 5. 5 minus 1 is 4. 4 plus 6 is 10. So 10 is stored at 4, and this is
0,
0, 3.
Mhm.
Let's look at 5. 5 is 2 raised to 2 plus 2 raised to 0. So starting from 4, the sum of starting from 4,
Starting from 4,
the sum
the sum of next one element. So it will be 4, 4.
of next one element will be stored at 5. So 5, and this is 4, 4. 6. 6 is 2 raised to 2 plus 2 raised to 1. So starting
Starting from
from
index 4, the sum. मैंने घेतला आपण. नाही.
4, the sum of next two elements will be stored at 6. So that's 9. And this is 4, 5. Let's try to fill up 7. 7 is 2 raised to 2 plus 2 raised to 1 plus 2 raised to 0. If you combine this two, starting from 2 raised to 2 plus 2 raised to 1, so starting from 6, the sum of next one element will be stored here. So that's minus 3. And this is storing 6, 6. Let's look at 8. 8 is 0 plus 2 raised to 3. So starting from 0, the sum of next 8 elements will be stored at 8. So that's 5. 5 minus 1 is 6. 5 minus 1 is 4. 4 plus 6 is 10. 10 plus 5 is 15. 15 plus 4 is 19. 19 minus 2 is 16. And 16 plus 3 is 19. So that's 19. And this is 0, 7. 9. Uh, 2 raised to 3 plus 2 raised
2 raised to 0. So starting from index 8, add one element. So it will be 8, 8.
to 0. So starting from 8, the sum of next one element will be stored here. So that's 7.
Mhm.
And we'll say 8, 8 is here.
Yeah.
10. 2 raised
2 raised to 3 plus 2 raised to 1.
to 3 plus
Starting from index 8, get two elements. So 8, 9.
2 raised to 1. So starting from 8, the sum of next two elements will be stored here. So that's 9. And that's 8, 9.
Mama, there was a problem.
And finally 11. 2 raised to 3 plus 2 raised to 1 plus 2 raised to 0. So starting from 8.
8 plus 2, 10, starting from the 10th index, get some of one more index, which will be 10, 10.
Plus to 10, the sum of next one element is stored here. The range is 10, 10. Alright, so hopefully you understood how I created this tree. I did not show you the efficient way of creating this tree, but hopefully this gives you an idea how I filled up the nodes of this tree using the prefix sum. So next, let's look at how we are going to search into this binary index tree. So our aim is to get the prefix sum given a range. So for example, give me the prefix sum from 0 to 5. So we want to get this prefix sum 0 to 5. So to get the prefix sum, you got to start from node 6. Because the end is 5, you start from 6. You go to node 6,
What?
0 to 5. Given a
Mama,
range.
Mama, this is not right. Yes, for fruits. Yes. Okay.
So for example, give me the prefix sum from 0 to 5. So we want to get this prefix sum 0 to 5. So to get the prefix sum, you got.
Right.
So our aim is to get the prefix sum given a range. So for example, give me the prefix sum from 0 to 5. So we want to get this prefix sum 0 to 5. So to get the prefix sum, you got to start from node 6. Because the end is 5, you start from 6. You go to node 6, you take that value 9. So the value here is 9. Plus, you go to its parent. So to go to the parent of 6 from 4, all you have to do is flip the rightmost set bit. So you come here, so that's 10. And then you flip the rightmost set bit and you reach 0. So that doesn't add anything, so 19. So 19 is the sum from 0 to 5 in my original array. So let's look at another example. Let's try to get sum from 0 to 9. So 0 to 9. So since this is 9, I'll start from the 10th node in my Fenwick tree. So I start from 10. So the value here is 9 plus.
If it's from 0 to 9, why do you start from the 10th node?
Plus I go to its node in my 9. So 0 to 9. So since this is 9, I'll start from the 10th node in my Fenwick tree. So I start from 10. So the value here is 9.
Okay, 10th node. Yeah.
Plus I go to its parent. So that's 19. And then I go to its parent. So that's 0. So that doesn't add anything. So this is 28. So the sum of 0 to 9 will be 28. Why this works is, let's see why it would work. If we're trying to get the sum from 0 to 9, we know that this 10th node here is storing the range 8, 9. So 8, 9 of this 0 to 9 is stored at 10. Also, we know that its parent 8 is storing the range, sum of range 0 to 7. Sum of range 0 to 7 is stored at 8. So the sum of range 0 to 9 is the sum of range 0 to 7 plus 8, 9, which is 8, 9 plus 19.
What if I want 9, 9? I don't have 9, 9 here.
Let's look at another example. So I was trying to get the sum from 0 to 7. So I start from 8th, so I was trying to get a sum from 0 to 6, for example. So I'll start from the 7th index. So 7 stores the sum of 6, 6. So this is coming. So I'll start from the 7th index.
Oh.
So 7 stores the sum of 6, 6. So this is coming from 7, so that's minus 3. Then I go to its parent, so that's 6. And 6 is storing the sum of 4, 5. So this is coming from here, and this is 9. Then I go to its parent, 4, and 4 is storing the sum of 0 to 3, and that's 10. So this value here is 16. So this is how we get the sum of 0 to 6 by getting the sum of 0 to 3, getting sum of 4 to 5, and getting the sum of 6. The amount of time it will take to get the prefix c will be the height of the height of this binary index tree, and in worst case, the height of this binary index tree will be O of log n. So the amount of time to get the prefix sum will also be O of log n. Next, let's look at how we're going to actually enter the values in this binary index tree in an efficient way, and how we're going to update the values in this binary index tree. Let's quickly look at how we're going to get a parent of a node. So I have the steps right here. Get this 2's complement of a number and this with the original number, and then subtract that result from the original number. Let's try to get a parent of 7. So binary representation of 7 is 1, 1, 1. 2's complement of 7 will be 0, 0, 0. Flip all the bits and then add 1 to it. So that's 2's complement.
And get with original numbers. First do 2's complement. So okay, for 7, binary representation is 8, 4, 2, 1. So 4, 2, 1. Then if you want to do a 2's complement, a direct method using pen and paper is to find the first rightmost bit, keep it same, and then convert all the other numbers to 0. So I have 2's complement for this here.
So that's 0, 0,
Number
1.
7, which is 0, 0, 1. Perfect. I have it. I have the same number here.
Then and this 0, 0, 1 with this 1. So that's 1, 1, 1.
And with the original number. And with 7, 1, 1, 1. And says that if there are 2 zeros, there's 0. Sorry, if you have a 0, the answer will be 0. Only if you have 2 ones together, the answer will be 1. So this is 0, 0, 1 only.
0, 0, 1. So this is 0, 0, 1.
Yeah.
And then subtract this result from here. So
Subtract from original number.
1, 1, 1 minus 0, 0.
So 1, 1, 1 minus 0, 0, 1, which will be equal to 1, 1, 0.
1. So that's 6, which is why 7 parent
Which
is
is, yeah, 4, 2, which is 6.
7th parent is 6.
Wow. So I need to remember these 3 steps to get to the parent. First, 2's complement. Sorry. First 2's complement, then AND with the original number, subtract with the original number. And we should be good and get the parent. Okay.
Let's try another example. Let's try to get binary representation. Let's try to get the parent of 10. So binary representation of 10 is 1, 0, 1, 0. 2's complement of 10 is 0, 1, 0, 1 plus 1. So this is 0, 1, 1, 0. Subtract and this with this. So this becomes 1, 0, 1, 0 and then 0, 1, 1, 0. So this is 0, 1, 0, 0. And then subtract this from this. So 1, 0, 1, 0 minus 0, 0, 1, 0. So this is 1, 0, 0, 0. So that is 8, which is why 10's parent is 8. To get the parent, or you do need to do these 3 steps, and that is an O of 1 operation. So to get the parent is O of 1 operation. Next, let's look at how we're going to fill up this table. Previously in the video, I showed you how I filled up this binary index tree from the original array. Let's try to do that efficiently this time. So we know that 0 doesn't store any information, so the only thing it has here is 0. Let's start from 1. So when I'm trying to fill 0, I try to fill 0 plus 1, so 1th node in my binary index tree. So I come here, I make whatever values here, we add 3 to it, so this becomes 3. But updating this 1 is not enough. You have to also update all the other nodes which could be affected. And to get those nodes, we'll use this formula get next. So let's start from 1. So 1 is, the binary representation of 1 can be written as 0, 0, 0, 0, 0, 0, 0, 1. Assuming.
Okay, to get next, we need to do 2's complement and with original number, add with 2 origin. Okay, we add here. And to get to the parent, we subtract from original number. And to get to the next, we add with
Efficiently
add to original number. Okay.
this time. So we know that 0 doesn't store any information, so the only thing it has here is 0. Let's start from 1. So when I'm trying to fill 0, I try to fill 0 plus 1. So 1th node in my binary index tree. So I come here, I make whatever values here, we add 3 to it, so this becomes 3. But updating this 1 is not enough. You have to also update all the other nodes which could be affected. And to get those nodes, we'll use this formula get next. So let's start from 1. So 1 is, the binary representation of 1 can be written as 0, 0, 0, 0, 0, 0, 0, 1. Assuming that we are storing 1 byte to store this information. So 2's complement of 1 is 1, 1, 1, 1, 1, 1, 1, and 1. If you add them together, this becomes
Yeah.
0, 0, 0, 0, 0, 0, 0,
1.
1. And if you add this with the original number, that becomes 2.
That becomes 2. Yeah.
So you go to 2, and you whatever value you set at 2, you add this number to that. So this becomes 3. Then find the next number that needs to be updated, next node which needs to be updated. So we repeat the same process again of get next. So 2's 2 can be represented as 0, 0, 0, 0, 0, 0, 1, 0. 2's complement of this is 1, 1, 1, 1, 1, 1, 0, and 1. And if we 0, 1, so 1, 0. If we AND it with the original number, this becomes 0, 0, 0, 0, 0, 1, 0. So this is 2. So we add this 2 to the original number, so we go to 4, and whatever number is there, we add this 3 to that guy, so that becomes 3. Then we again use the same formula, 4, 4, and get the next one, which will be 8. So this will also become 3. And then we go to use the same formula to get the next after 8, and that will be greater than 11, so we stop the process. So we have updated
Wait,
3,
what?
and then, so that becomes 3. Then we again use the same formula, 4, 4, and get the next one, which will be 8. So this will also become 3. And then we go to use the same formula to get the next after 8, and that will be greater than 11, so we stop the process. So we have updated 0 here. The amount of time it took was O of log n. If you look at how many nodes I had to update here. Let's start with 1. So now I go here. So I'm going to update 1 into my binary index tree. So for 1 I go to 2. So the value for 2 is 3. So 2 plus 3, this becomes 5. And then I need to update everything after next of 2. So next of 2 is 4. So this becomes 5. And next of 4 is
Wait.
everything after next of 2. So next of 5 into my binary index tree. So for 1 I go to 2. So I go here. So I'm going to update 1 into my binary index tree. So for 1 I go to 2. So the value
Yeah. For index 1, we go to the node 2. Yes. Update its value.
so that 2 is
And then now do 2's complement, which is what is 2 first? 2 is 0, 1, 0. So its complement will be 1, 0, 1, 1, 0. Do a 2's complement, perform a AND with the original 1, 1, 0 and 0, 1, 0. If we AND, we get a 0, 1, 0. Again, it is 2 and add plus 1, which is 3. So go to the third node.
3. So 2 plus 3, this becomes 5. And then I need to update everything after next of 2. So next of 2 is 4. So this becomes 5. And next of 4 is
Wait, why did I get 3? I should get
0, 1, 1, 1. And if you add this to the original number, that becomes 2.
and this is, yeah.
So
This is the 2's complement and with original number. This will be 1 and then add. This
you
is
go to
2.
2, and you whatever value you set at 2, you add this number to that. So this becomes 3. Then find the next number that needs to be updated, next node which needs to be updated. So we repeat the same process again of get next. So 2's 2 can be represented as 0, 0, 0, 0, 0, 0, 1, 0. 2's complement of this is 0, 1, so 1, 0.
Yeah.
If we AND it with the original number, this becomes
2 again.
0, 0, 0, 0, 0, 1, 0. So this is 2.
Oh, add to original number. Okay, so we do plus 2 here, which will give us 4 at the original number, not add 1, but add to original number. Okay.
Let's start with 1. So now I go here. So I'm going to update 1 into my binary index tree. So for 1 I go to 2. So the value for that 2 is 3. So 2 plus 3, this becomes 5. And then I need to update everything after next of 2. So next of 2 is 4. So this becomes 5. And next of 4 is 8. So this also becomes 5. And next we are getting using this formula.
Let's see after 8 what do we get. 8 is 4 to 8 4 to 1. 8. So 1 0 0 0. This is 8. Now 2's complement for this will be 1 1 0 1 1 1 0 0 0. And it with the original number we get 0 0 0 1 0 0. Okay. Now we add plus 8. This is this. Okay, so we get 16, which is greater than our node level. So, okay. So we exit. We move on to the next index from this array. Okay.
So next, let's look at, and after next of 8 is greater than the length of this binary index tree, so we stop. Let's look at 2. So for 2, we go to 3, so this becomes -1.
For 2, we go to the third node. Okay.
Next, we'll see which is the next number that needs to be updated. So the next of 3 will be, binary representation of 3 is 0, 0, 0, 0, 0, 0, 1, 1. So 2's complement will be 0, will be 1, 1, 1, 1, 1, 1, 0, 1. If you add them, it becomes 0, 0, 0, 0, 0, 0, 1.
Wait, this should be 1, this should be 0. This should be 1, this should be 1 as 1. Oh, wait. 2's complement for this, yeah, then this is correct.
So this is 1. So you have to add 1 to the original number. So 3's next will be 4. So you go here and this becomes 5 minus 1, 4. And then 4's next is 8. So this also becomes 4. And then 8's next is 16, which is outside the range. So we stop. Then we go to 3. So to go to 3, we come here and we update whatever is at 4 plus 6. So that becomes 10. So which is out. And then 1 to the original number. So 3's next will be 4. So you go here and this becomes 5 minus 1, 4. And then 4's next is 8. So this also becomes 4. And then 8's next is 16, which is outside the range. So we stop. Then we go to 3. So to go to 3, we come here and we update whatever is at 4 plus. So this next is outside is 3. So this becomes 3. Apply this formula. If you are going to update 7, go to the 8th node. Then you put the value there, add whatever is there plus this value, and then they get the next value. And if that next value is in the range of this binary index tree, update log of n. Since we are doing for every operation, it's taking O of log n time, and since there are n elements, the amount of time it will take to create this binary index tree will be n log n. Finally, let's look at how I'm going to update a value. Say I came over and I updated 3. So this 3 becomes
Just a moment. Hmm. Why?
so the value at 3, so 6 becomes say 9. So the difference between them is 3. So I need to update this 3 all over my binary index tree. So again, I start from 4. So I go to, so 3 plus 1, 4. So the difference here was 3, so I add 3 here. So this becomes 30. Then 4's next is 8. So we go here and then this becomes 22. And then 8's next is outside the range. So again, the amount of time it took to update it, any element will be O of log n. Let's try another number. Let's try to update 4. So we go to 4, so this becomes 10 range of the binary index tree. So as you can see, the amount of time it takes to update any value and into this binary index tree is O of log n. So this is all I have to talk about the Fenwick tree or the binary index tree. The link to the code will be in the description section of the video, so you can just go to the link and see the code, and it's exactly same as I discussed right here. Also, you can check out my GitHub link, github.com, mission piece intro wiki, and you could also subscribe my YouTube channel, youtube.com, user tushar2525. Thanks for watching this video.
Think of Kafka.
Are you a
Bhai. Hello. Hi guys, good morning. Welcome back to a new video. In this, we're going to see Fenwick
Okay.
trees. Now, it is not like other videos in which you are always confused how actually the Fenwick tree is working, how it is solving my problem, what was the problem, how it is solving it, and actually how the code is replicated with the visualization of how Fenwick tree works. That's the reason in interviews you might forget the implementation of Fenwick tree because the instructor has never taught you how to think about it. So yeah, let's begin and see what is actually a Fenwick tree. Now, before even seeing what it does, all that stuff, let's firstly see where it is actually used. Maybe in future you just want to bookmark it, then you can bookmark it that okay, in all these places I can actually use my Fenwick tree. So Fenwick tree, also called as binary indexed tree. You will get to know why it is called a BIT, binary index tree, but it's mostly used to find range calculations. For example, range sum, range maximum query, which means in a range. Again, range sum
Range max query. Okay.
means that in a range you have to find the sum of the elements in a range. In a range you have to find who's the maximum element in the range. In a range you have to find who's the minimum element in the range. In a range you have to do some XOR operations. Mostly range queries can be done by Fenwick trees, but the other applications which you can see are inversion counts, which is a very famous interview problem which is asked in an interview. And this problem we will actually also see in the next video also, which is the application of this particular Fenwick tree. Now, we saw that you told that okay, you can do range sum operations, but I have also heard about sparse tables, and I've also heard about prefix sums, which is the most commonly used range sum operations. And for the folks who don't know prefix sum says if you have a nums, then you will take the prefix sum, as the word says, prefix. 2 plus 1 3, 2 plus 1 plus 3 6, 2 plus 1 plus 3 plus 4 10. So this is I'm taking a prefix sum and then plotting it here. Because of this prefix sum, let's say if you ask me and tell what is the range sum of this j to i, then I'll say okay, I will go and pass that. I will do is now I will update your nums itself. After every, if I go and ask you, bro, what I will do is now I need anything else because you just most optimal time you can actually achieve. So why you need anything else? Because you would need, if I go and ask you, bro, what I will do is now I will update your nums itself. After every query, I'll update your nums. Although I'll ask you, bro, what is the range sum? But then I'll go and ask, bro, do one thing, update this 3 to 4. Then what you will do? Will you go and update your entire prefix sum again? Which means you will have to go and update the entire prefix sum again. So okay, 2, 3. Now every small element, one element update, I have to apply again an O of n operation to update the entire prefix sum. How is this even useful? Like you're using O of n operation to apply the prefix sum again. So for that, people thought of okay, I have to apply on the entire range again. Rather, can I bifurcate the range? Which means can I like have a division in the range? So earlier, rather than having the entire prefix sum, I will just break it down. Okay, I will have a prefix sum of 3 elements and then prefix sum of other 2 elements. So you will see if I just plot my existing elements prefix sum, so 2 plus 1 and 2 plus 1 plus 3, 2 plus 1 and 2 plus 1 plus 3. Then although earlier I was just going ahead, but now I have broken down. Okay, 4 plus 5 9. So you saw that I broke my prefix sum array itself. Aryan, why is it useful? It is useful because earlier when you were updating this 3 to a 4, then you will have to update the entire prefix sum array. But now you know it is broken at this point and you updated this specific element. So you only have to update this specific prefix sum array. That's it. So I'll only update this specific prefix sum array. I will not touch this later part. So what will happen? It will become a 2, 3 and 7. Now, same, if I go and ask you, bro, what is the range sum for this portion? You will go and ask, what's the range sum in this portion? Sorry, what's the range sum in this portion? And what is the range sum in this portion? Same way, for the updated one, what's the range sum in this portion? What's the range sum in this portion? Range sum in this portion is 4 minus 0. Range sum in this portion is 7 minus
2. Okay, just working. I just want to see my track for today's weekly contest. 3007. Okay, it's pretty good. I think my rank will increase, my rating will increase. I mean, obviously, it will increase because I usually get 7,000, 1,000 ranks. from 38 to 62. Yes, 38, 24. Okay. I'm currently at 1665. Hopefully it increases. I mean, it will increase, but let's see by how much.
2. So ultimately my range sum will become actually 9. So that is the actual backbone idea of my Fenwick tree. That I wanted something like of a prefix sum, but I cannot afford to keep on updating the entire array again and again. So what I will do is I will break this entire array down into some segments. Again, the actual idea, Aryan, okay, now I got it. Okay, I will break these segments, and because of breaking, I might optimize my time. How much? That I'm not sure of. So that is the one question I will think of. But meanwhile, can you tell me how I'll actually break it? Because breaking, how you will break will define how optimization you can have it in the time complexity of this specific range sum which you will get. So now my thought of, okay, breaking is a very standard phenomenon, and we have seen many such videos of people breaking in half, and then whatever is remaining, then we again break in half, then again break in half. Why people always keep on breaking in half? Because half is actually nothing but a
Log
base 2 operation. So if I just break anything in half, I know for sure that ultimately I will require log into the base 2 number of operations. And that is, I reduce the complexity from O of n to O of log n to the base 2. Oh, so what I can do is I can actually make my ranges as half. Like I can just try to break my ranges in half or basically in a power of 2. But again, that seems fine, but still, it is not understandable that how you actually make. Okay, let's say if this was your actual input array, and if I ask you what the range sum of this specific portion, how will you find it? That's a good question. So which means I'll go very basic. I'll go very basic. Okay, what if you asked me only first, again, let's take another color, but what if you asked me this one element sum? So okay, which means that I should be having one element as a sum. So what I will do is I will keep one element as a sum track. Okay, one element sum I'll keep track. Now, what if Aryan, you ask me these two elements sum? And I was saying to you that I will keep my sums in a power of 2.
We are looking for 100.
Which means I'll just try to replicate my log n kind of complexity. So I need to break my sums in a power of 2. So yeah, it is good to know that I will just get this as, because I know it is 2 elements, so I'll get it as one sum. Okay, 2 I'll get it as one sum. But Aryan, what if, okay, this you got, this 2 you got, but what about if you want to get this? Oh, if you want to get this, then you have your 2 sums. If you have your 2 element sum, you have your 1 element sum, you can just simply subtract to get the just this specific element sum. Aryan, it is just 1 element. Why can't you take from the input array itself? That is obvious question, but hold on, keep on going. You will see why I'm not taking it for as one. That is for the sums in a power of the sum of the 4 elements. That's how I'm trying to build my prefix sums. Kind of, you can just imagine that, okay, this will store the sum of the 4 elements. How I know I want to show the sum of 4 elements? Because I know I will store the sums in a power of 2. Okay, great. Now, again, can you please go ahead? Which means, let's say if I go and ask you if I want to take this specific sum, it's 2. So it's 2. So are we saying that it is 2? It is 2. So are we saying that we have to also keep track of these 2 sums? I'll say no. Why? Because you want these 2 as sums, right? So what I can do is I have these 4 as sums. I have these 2 as sums. I have these 4 as sums. I have these 2 as sums. Then I can just subtract them and simply get this. Oh, great. So basically, I'm just keeping track of just one sum here. Okay, one sum here, 2 sum here, 4 sum here. Again, I'll just keep track of one sum here, not 2 sums. Again, I keep track of two sums here, and that is how I'm trying to keep track of some range. Again, range is another power of 2, and I'm only keeping track of those specific sums which are actually useful for me. If it is now, how to know if it is not useful? If I can just derive that specific range sum value from some other values, then there's 4 sums which I've taken. I will subtract it minus 2 sums, so I'll simply get this specific these 2 sums value. So now you have got a rough idea of how this Fenwick tree logic is actually built on backend, which means it tries to get the range sums in a power of 2, and those specific range sums are only and only, again, it is actually just a sufficient number of range sums that is required for you to get any specific range sum value. Let's say if I ask you, you want to get this specific sum, again, you will see that it has no intersection at all. So what I can simply do is I will get this sum, I'll get this sum. This sum you can simply see I have already stored that as one sum. This sum I have not stored it anywhere. So what I will go is I know one thing for sure. I have this 4 sum values. This is 4 sum values. I subtract the 2 sums from it. I subtract the 1 sum from it. And ultimately I'll get the just last remaining sum. So that is how I'm actually keeping track of only the most sufficient values. Range sum values. Now coming on back, that is the basic crux of how actually you will use a Fenwick tree to find any possible sum.
That will be of one, what do you say, range queries. Yeah, queries. Yeah, it will be of 1 queries. So, which is pretty efficient. Yeah. Okay. Is my audio good? Why is it lagging? But no. It's loud for a second. Okay. Never mind.
Sums. But Aryan, please let us know how you will make the sums, because it seems very optimal, but how you are making it. Back very carefully in this. That next time I was keep it like again for the first time. Like okay, keeping this one sum, skipping that one sum, skipping that one sum, skipping that one sum, skipping that one sum, skipping that. That is how I again. You can easily see that's the entire diagram of the 16 values which you have. Or you can say 15 values for you to actually visualize. So as you can easily see, I am keeping track of one sums alternatively, and I can easily infer from this above diagram also. Again, just only keep track of those sums which you actually need, and I have derived, I have shown above that what you actually would be needing. Now, okay, one sums I have done, and I have plotted again. Let's imagine this sum as a bit array. Let's imagine this sum as a bit array, which I can use to find out any range sum values, and I'm trying to build this bit array itself. Okay, one sum is done. Now, next comes the two sums, because I know that I have to break my array into.
Hello. Hello. Trying to handle
A power of 2s. So I need to actually build it in a power of 2 also. So 2 is for 0, some range is done. 2 is for 1, some range will now come in picture. Here. Okay, so similarly, I'm just trying to again use some funda. Again, this is a logical way to understand this. I will tell you in the code also how the code is actually implemented for that, but understand this logically right now. Now, I'll simply go and ask, bro, I want the 2 sum range for me, for this me. I want the 2 sum range, which means I want these 2 sum. I want a sum for them. So I'll simply grab 2. I'll simply grab 2. I'll add that with my previous value. I'll simply, again, add not this value. I'll specify, no worries. Puts next to one element. You will keep track of the 4 element. You will 9 plus 7. In the 4 sum values. Again, skipping the next 4 sums, it's a power 1. So specific value is n. Then you just go backwards log n times. That is how actually it is useful. That coming back, we'll skip next 4. Okay, no worries. The 8 sums also. Do a range sum of next 8 values. So now you can see simple range for you to understand. You're asking for 1 to 7. This is the range. 4 value, which is this specific value, being stored at this specific locations. So what I will do is, again, this is the natural, this is the normal array, but the bit array corresponding to that I have already made above. If you have known, I've already made this bit array. Bit array is already made above. Now when this array is made for me, I know one thing. One sum, again, I want the from 1 to 7. I want the range element. So what I will do is, I will get this specific sum, one sum. I'll get the next 2 sum value, which is this specific value. I'll get the next very lazy propagation in segment tree. It becomes very big code. For the folks who don't know what all that stuff, just forget that part. That is always propagation. And if you add lazy propagation in segment, it's a very long code, because it will be very highly unlikely that you will be implementing a segment tree, because it's a very long code. Because segment tree itself not great unless you apply lazy propagation, and if you add lazy propagation in a segment tree, it becomes very big code. For the folks who don't know what all that stuff, just forget that part. So that's the reason I always recommend using a Fenwick tree. Very short and simple 3 propagation tree code. It's just 3. How it will look like? Simply, again, I'm just showing you the code, but I will explain that code also. So the code is very short and simple. That's the reason I don't prefer you will be in propagation with that part. So that's the reason I always recommend using a Fenwick tree. Very short and simple 3-4 liner code. So if you want to query, I will go and ask again, Aryan, you have only passed in one argument. Aryan, you have only passed in one argument, which is ID. What does ID means? I was about to calculate the range sum. No. Oh, this ID means that you will find the range sum in the range of 1 to that specific ID. Okay. But Aryan, don't we have a liberty to find the range sum of L to R? Are we always finding the range sum from 1 to R? Bro, if you want to find the range sum from L to R, just go
Subtract R minus L minus L minus 1.
and find the range sum from 1 to R. Just go and find the range sum from 1 to n minus 1. And then subtract that. Simply get the answer. Simply get the answer. How it is such a big deal? No, right? That's the reason. I'll find the range sum from 1 to ID. How I'll do that? I will use this kind of formula. Again, it's the shortest possible formula written. I will expand that and tell you. But for you to understand,
Yeah, I get it. The first we take a 2's complement, then for query, right? For query, yeah. We take 2's complement, we AND with the original number, then we add with the original number. But here I guess he's finding the parent or something. Oh yeah, from 1 to ID. So we need to move backwards. So I think we should take a 2's complement and with the original number and then subtract with the original number. This is and this is 2's complement, and we then subtract with the original number. Okay, this makes sense.
Please understand some
Okay.
basic concept of bit manipulation. ID
Answer.
is
Okay.
simply, again, ID is simply a number, integer. But to explain that, I will convert that to a binary form. Minus ID is again a negative integer of same ID. But then how, again, as I spoke earlier, I will convert ID to a binary form. How a minus ID is converted to its binary form? By using its 2's complement. By using its 2's complement. How it is done? Simply flip these bits, flip the natural bits which you had, and then add a 1. You will get a 2's complement, and that is how you represent a negative of a number, right? 2's complement, say simply flip the bits of the original number, which is positive numbers, add a 1, you will get a 2's complement, and that is nothing but a minus of that specific ID. That is the basics of bit manipulation, which I'm teaching you right now. Now, AND operation is nothing but ANDing these two binary numbers which I have got, and then minus is nothing but whatsoever you have got by doing a AND, subtract that from the original value. Again, it's a normal subtraction operation. So this operation is entirely which this line is doing.
This was me about a decade ago.
That's the reason. It's so short and simple. Although it might seem complex idea, but no worries, you'll understand that. But in Crux, what it does is it removes the last set bit. I'll make you sure that you understand that part. But you're simply adding the current. Now, what will happen with this is you will see that you were at, again, I asked you to find the range sum of 7. 7 in the binary form is 1, 1, 1. So as you saw that you will add this value, right? You will add this value, you will add this value. Again, you will add these values from your bit array, not the natural array.
From the bit array, yes.
Because in bit array you would have computed the sum, but right now I'm showing it from the natural array for the reference. So what this operation will do is, again, don't go into very deep. I'm just showing you in deep. I will let you go. I will take you deep, not that deep, but yeah, I'll take you deep. What will happen in this is you are adding, again, ID is initially number 7. Binary form number 7. So you will add that in your answer. You added this specific value in your answer. Okay, added that value. Now, this operation will remove the last set bit. Your 1 is gone. You will get a 110. Okay, 110 is the specific number. So you will add this specific value. This specific value I've added in my answer. Added next value. Again, value will keep on going until my ID is not equal to 0. Now, you will again this operation right here will remove the last set bit. Last set bit is this specific one. It is removed. You will get to a 100. Again, add this specific value, which is this specific value added. Now, when this is done, you have added the value ID, remove the last set bit. Last set bit is removed. It becomes a 0, 0, 0. 0, which means breakout. So you have added these 3 values in your answer, and that's how you actually perform your query operation. Now, when you understood this, let's quickly go and understand deep by deep how in the binary form, which is diagram, this specific example itself. Query for 7. Query for 0, 1, 1. I simply asked, bro, can you please query for 7? If you remember in the loop itself, I just firstly added the bit value for that specific ID. Bit value for that ID, if you had remembered, again, bit values are above. Take a snapshot of this for your reference. Bit value is above. So this is the bit value, which is 10. Again, this is the bit array. For your reference, I have made the bit array, but I will keep the reference of the original array for you to show how original array from the original array I'm just getting the answer. Okay, from the bit array, I have got a value of 10, which was value of 10, right? Okay, I just get that value 10 and add my n in my answer. Now I have to apply this operation, which was this, and I know this operation removes the last.
Wait, what is a bit array?
Okay, 2 sum bit array, 1 sum skipping 1 element. Why you are adding the previous value right here? You can also add the previous value right here. Yeah, makes sense, but you will understand why I'm adding this specific value using my already computed bit to find my new answer. So I'm adding my 2. You still argue. Now,
Okay.
same way, I have
Basically, that this is bit array means this is the Fenwick tree, basically.
again, I computed it, and then I went on to again, as I was skipping 1 element, 2 elements. Then I'm again going on to again. You can
Okay, this makes sense.
element, and that is nothing but a minus of that specific ID. Got by last side bit is this specific one. It becomes a 0, 0, 0. Go and under 0, which means breakout. So you have added these 3 values in your answer, and that's how you actually perform your query operation. Now, when you understand in your answer, quickly go and understand you actually perform your query operation. Now, when you understood this, let's quickly go and understand deep by deep how in the binary form, which is there in this specific example itself. Query was 7, query was a 0 1 1. I simply asked, bro, can you please query for 7? If you remember in the loop itself, I just firstly added the bit value for that specific ID. Bit value for that ID, if you had remembered, again, bit values are above. Take a snapshot of this for your reference. Bit value is above. I have made the bit array, but I will keep the reference of the original array for you to show how original, right? Okay, I'll just get that value 10 and add my n in my answer. Now, I have to apply this operation, which was this, and I know this operation removes the last n in my answer. I have got a value as 10, which also how for your reference I have made the bit array, but I will keep the reference of the original array for you to show how original array from the original array I'm just getting the answer. Okay, from the bit array I have got a value as 10, which was value as 10, right? Okay, I'll just get that value 10 and add my n in my answer. Now I have to apply this operation, which was this, and I know this operation removes the last set bit. How the operation works is that you have your ID, which was the binary form of number 7. Then you have to apply this operation. How the operation works is ID was 0 1 1. Minus of ID will be 0 1 1. If I flip the bit, it will become a 1 0.
0 1 minus ID will be 0 1 1.
0 0, right? 1
Ouch. Yeah.
1 0 0. If you remember, but I told you flip the bits and add a 1. Flip the bits, add a 1. So it will become a 1 0 0 1. By adding a 1, it becomes a 1 0 0 1. Now, when you have this and this, simply do a AND operation between them. After doing an AND operation, I have got this specific value, which is 0 0 0 1. This is the AND value. This is the AND value. Now, when you have got this value, simply subtract this AND value from the original ID. Original ID was 0 1 1. Remember that fact. Again, remember it, or maybe dry run with me, which means take a pen and paper with me. Visually last said. Do is you have got your ID, new ID as 6. Again, when your new ID is 6, go and ask your bit array. Your bit array will give you this specific value, which is 25, which is the range sum of these two values. Again, add in your answer, act the same operation, apply the exact same operation, your ID will become a 4 now. Okay, go and ask for the 25. This was a 1. Let's see the value, and I added this value, a bit of 1,4. And that's how you've got the range values. Again, this, a number will have just log n bits. So I'll for sure will break down into log n, at max log n number of ranges. So that's how I know the time complexity for this operation. Again, we know that we have at max log n number of bits for that specific number. That's the for sure the loop, because see, it is nothing but a loop. It is nothing but, if you go back, it is nothing but a loop, ID, while loop, which actually removes the last set bit. And I'm saying a number can have at max log n bits. So at max you can remove log n bits from the range sum. Any point. That's how number can have at max log n bits. So at max you can remove log n bits from this number n. And that's how you know one thing for sure, that you will apply this operation log n times to find any portion. This is the exact same code of query. But Aryan, this is a code for query, which means this code can only be applied after I have built my bit array. How you will build the bit array itself? Let me know. Let us know that also, right? No worries. The actual, if you want to build your bit array itself, again, the code for this is exactly same.
This is for queries, okay.
Right? For the query, for the range query. But to build the bit array itself, I'll simply use the.
We need to find next. Yes, so we do a plus here.
Reverse code, which means if you look,
And it should be within range. Oh. Okay. This is the ID where it needs to be placed. This. This is the value that needs to be placed at this ID. Bit ID plus equal to this value, and then perform the operation. Okay.
back this code. You had your ID, you was removing those elements and adding that in your answer. Now I will use a reverse funda. I will, from the number, I will keep on adding that. But I will about, and you are fast in it. So what I will do is, you'll have learned a part of it, right? That's the reason. So remember this, so that you are fast in it. So what I will do is exactly the same. As you saw, that I'm simply adding my answer, the bit value. I'll simply, in my bit value, I'll simply add the value itself, because I'm updating it. As you can see, updated. This simply says updated the index with that specific value. I'll tell you what that means, but right now it says operation is update that specific index with that specific value. So until, because I'm starting and going on updating, so until it reaches the end, Again, you just remember that it's simply a reverse of the query. Query is you're simply reducing your I, and update is you're simply increasing your
Increasing your ID.
I. If you increase something, then you will simply make sure that it is reaching n. If it reaches beyond n, you'll simply stop. That is the funda I told you for learning this specific piece of code. Now, I'll make you understand how it is actually working. So, if you had gone and remembered, if I go and ask you, you have to build a specific bit array. Now, first time you encountered the element 5, you know that at what all places my 5 will have a contribution. If it's a sum of 4 elements, I wanted the range sum of 8 elements. So, you can see this 5 is contributing in the range sum of 1 element, 2 element, 4 element, 5, and this 8 elements. So, I'll do the same thing. I know that this specific 5, again, remember this pink 5. This 5 is nothing but its bit value, but remember this pink 5. I'm showing you how this pink 5, where all places he will go. This pink 5, he knows he has to go on to one range sum. Okay, one range sum he has gone. Range sum for 2 values, he has also gone there. Range sum for 4 values, he has also gone there itself. And range sum for 8 values, he has also gone here itself. Oh, great, Aryan, great. But Aryan, what this goes means, you can see that. Let me just iterate one more, then I'll show you. So now, for the specific 2, if you remember that, this 2 also will go some places. It will go in this 2 range sum. It will be included in this 4 range sum. It will be included in this 8 range sum. Makes sense? So what happened? This 2 went on to this 2 range sum. This 2 went on to next 4 range sum. This 2 went on to 8 range sum. Oh, great. So you saw that this specific bit value will be 5. This specific bit value will be 5 plus 2. So I am doing one thing. I know the index is index 1. One, you have the value how you're acting that for you that 0 1. ID and minus ID, I have got this specific in any range L to R. Aryan, but you showed the update from 1 to R. I'll show you that I've shown update from 1 to ID. But you can bifurcate, and we have from 1 to R minus 1 to L minus 1, right? And we have seen that we can do a point update. Aryan, this is never show, bro, the entire to L minus 1, right? And we have seen that we can do a point update. Aryan, this is never show, bro, the entire code is update code, right? You just have a specific ID. You have a specific ID, let's say 1. If I want and say that, okay, at index 1, I add some value 2. So at next one, rather than 5, I want to add a value 2. So now I added a value 5 plus 2, it becomes a 7. So now I'll simply propagate that value, which means the plus 2 which I've added, I'll simply propagate that to all the bit values also. One quick fact, people get confused in this is that, Aryan, that seems okay, but I cannot modify this code according to the demand of the problem. Right now, you updated the value, which means you added something in your existing value, right? But what about the problem is saying me that you modify this, which means instead of 5, put a 7. How about I will do it? Now, one group of people will come and say, hey bro, find the difference and do it. I'll say do one thing. You have to make the contribution of this 5, because see, you are removing this 5, so you have to make the contribution of this 5 as 0, like as nothing, right? Do one thing. You have already made this update. Now to revert the contribution of 5, just simply apply the same operation by saying at the ID of 1, apply minus 5 as the update value. So what will happen? The contribution of 5 will go away, and now when the contribution of 5 has gone away, now do the actual bit, which is value of 7. That's how you can actually use the same piece of code to modify stuff. If I ask you, just update the value. Okay, it was a 5, update the value plus 2, like add a plus 2 or subtract a minus 2 or subtract a plus 2, which means or do a minus 2. Then you'll simply do okay plus 2, because you can simply see how it is impacting. It is adding in your existing bit values. So whatever you are bringing in, it is simply adding in the existing bit values, right? So that's how you can actually modify this simple piece of code to meet your own demands. Now, so we have seen that we can do these operations. Now the code is exactly simple, exactly same. Again, keep this code as a snippet with you, or you can just make sure that you can actually write this code very fast, because it's very simple code. Firstly, I will initialize my n, right? Why is n needed? Because you know that you need to go up till the limit of n. Now, what is this n? N is the size of your array, for which you have to make the bit array itself. So if you remember, our main function will look like that. I will make a bit array. Again, this bit array is also global. I'll make this bit array the size of n plus 1. Array y plus 1, because I told you your array is 1 indexed. If your array is 1 indexed, you will have n plus 1 indexes. So I will make my bit array also 1 indexed. Again, here I have put in my a array also 1 indexed, but your a array can be a 0 index. If it is a 0 index, make sure you populate the correct bit array. Your update will always be 1 based. Your bit index is always 1 based. Make sure that part, write it down, else you will get things wrong. Update will always be a 0 index. I'll make this bit array the size of n plus
1.
1. Array y plus 1, because I told you your array is 1 indexed. If your array is 1 indexed, you will have n plus 1 indexes. So I will make my bit array also 1 indexed. Again, here I have put in my a array also 1 indexed, but your a array can be a 0 index. If it is a 0 index, make sure you populate the correct bit array. Your update will always be 1 based. Your bit index is always 1 based. Make sure that part, write it down, else you will get things wrong, very wrong. So your I will be from the 1 itself, and I'm just updating my entire, I'm just in the very beginning, I am inputting my elements of nums, and I'm trying to build my Fenwick tree. which means contribution of every element. In the if you remember, the index 1 I have 5, index 2 I have next values and stuff. So I'm just simply updating my bit array because of this update function every time. And this will make my entire Fenwick tree for me. Now I can simply go and ask for the queries. My query will look like, again, the actual essence of Fenwick tree is when you are updating the nums array. If you're not updating it, you're only querying it, if you're only asking for a range, then always apply prefix sums. It is much more efficient. But if you're not updating it, you're only querying it, if you're only asking for a range, then always apply prefix sums. It is much more efficient. But if you have to update something, then please go and apply your Fenwick tree. Great. So now type 1 query is, please go and find the sum in the range L2R. Please go and find the sum in the range L2R. When you have to go and find some range, go, as I told you, go and ask for query of R minus query of L minus 1. Because you remember, query will give you from 1 to R. Query will give you from 1 to L minus 1. And you have to go and find for L2R. And simply get the answer. And if you want to do a replace function, again, it's a replace function they have given, which means replace the index value to some new value. So I told you, if you have to replace some value, first simply remove the existing of the existing value. So existing value was minus of existing value was a of id. I removed its existence by doing a minus of aid, and then I updated its existence with the a of id. Okay, that is how I can do it. It's a new value. It's a new value. It's a new value which I've got. And as you can see, I've updated a new value also. It's a new value. Now, the main functions of query update will be exactly same. The update will simply go and the exact same function up value. Now, okay. That is how I can do it. It's a new value. It's a new value. It's a new value which I've got. And as you can see, I've updated a new value also. It's a new value. Now, the main functions of query update will be exactly same. The update will simply go and the exact same function update up till on to log and hops. I am doing update for all the n operations. I will use a log n time because I know I can still have log and hops backwards. So it will be q log n for the two queries which I have. Space is again O of n because I'm just building a bit where we have seen. Now, for the complexity part, we have seen that each update function will go on to log and hops. So each update will take log n steps. And in the very beginning, if you have seen, I am doing update for all the n operations. So for sure, n log n will be for sure there as the time complexity to actually build your bit array. For every query command, I will use a log n time because I know I can still have log and hops backwards. So it will be q log n for the two queries which I have. Space is again O of n because I'm just building a bit array of size n plus 1. That's it. And that's how you can actually use your Fenwick tree. Now, there is a question which is a hard question, but it's a very, very easy question which you can do as a practice after watching this video. And its actual implementation, like its entire code, we will bring on in the next video, which is a part of our 100 days, 100 question challenge, right? In which we discuss the famously asked questions. And right now, we have just seen point update and point query. Sorry, we have seen point update and range query, right? We still, because of simple code of Fenwick tree, we still can use a range update and point query, which also your segment tree can do. But range update and point query, which also your segment tree can do, but then you would need your lazy propagation. Range update and range query and point query, which also your segment tree can do, but then you would need your lazy propagation. Range update and range query, again, segment tree, lazy propagation. So for these two, we have to use segment tree for lazy propagation, but because of Fenwick tree, we can also make its code very short and simple. Although its code, because in this you have to use two Fenwick trees, it might look complex, but it is much, much easier than that of your lazy propagation. It is also very, very, very easy. Very easy. A very slight modification in existing code and you will get it. Again, if the video not comes in and if you still want to learn these two remaining ones, then just go on to cpalgorithms.com. Just write on Google CP algorithms. You will get a website page. In that, search for Fenwick tree. You will get these two variations also. Don't study from anywhere else. Everywhere else, it's such a bullshit and such a crap code. The piece of code is so beautiful there. Cool. That's it from me. Thank you for watching. Bye bye. That's a long video. Bye bye.
70 minutes.
A bit delayed because the work is too much right now. A bit delayed because the work is too much right now, especially of office also. So the problem simply says that we are given an integer array. It's very short. Problem.
Count smaller number of yourself. Okay. Give the integer array nums return an integer array counts where counts I is the number of smaller elements. Number of smaller elements to the right of nums I, and nums dot length is 10 power 5. Okay, this is big as well. Okay, I'll go to the washroom and be back. So yeah, I'll be back. To the washroom. Okay, let's go.
Integer array nums, and we are also, when we have to return an integer array called as counts, where counts of I is the number of smaller elements to the right of my nums of I. What he mean by it is, let's say for example for this number 5, I have to return this count array. What this count array means, after this 5, which means in the right of 5, how many elements are smaller than 5? I can see there are 2 elements, 2 and 1. So for 5 the answer is 2. 2 and 1, count is 2. For example, same way for 2, for number 2, count of smaller elements to the right of 2 is just 1. Okay, answer is 1. Now same way for 6, count of smaller element to the right of 6 is just 1. Okay, answer is 1.
Okay, if I didn't know Fenwick tree, I would solve this using monotonic stack. I think we can come up with a solution using monotonic stack, where you just see, but you don't know the count, right? Oh no, we can find the count. How many numbers that are smaller? Yeah, just start from here. If 6 is greater, add it into the stack. Now, before adding this into the stack, check the size of the array, sorry, the stack. Count of smaller numbers after set. Where count size? Yeah. So yeah, this is 1. Perfect. This, now in the stack we have 6 and 1. Let's see. Initially in the stack we have 1. We come to this index, we see a 6. But before this, we check whether or not the top element here is smaller than 6 or not. If it is smaller, we are good. We should just check the size of the stack and add it into this nums. If not, just just remove um yeah, but if we remove all the smaller numbers, sorry, all the greater numbers from 6, what if the array look like 7, comma 2, comma 6, comma 1? Then we are 6, and then suppose we have 7 here, we have 8 here. We look at 1, we have 1. Then we look at 7. 7 is small, add it into the 7 is bigger than 1, add it into the stack. And in the place of 7, we add 1, which is the size of the stack. Then we come to 6. We see that 7 is greater. We remove 7. Check the size. We have 1 in the 6th index. Not the index, in here 0, 1, 2. In the second index, we add the value 1 here in the output array. Then we come to 2, 6 is bigger. Boom. we again have one element which is smaller than this. But the problem arises when we have a number like 8, which is bigger than all of these numbers. When we were at 2, we removed 6 and 7. Why? Because it was bigger than 2. So for this index, okay, we can agree that 6 and 7 uh won't count, right? And only one will be there, which is smaller than 2. So it will contribute to the count. But here, in 8, if we have 8, we when we were at 2, we greedily removed 6 and 7 and kept 1. So being greedy, using a greedy solution like this won't give us the correct solution. So when we are at 8, in the stack we only have 2 comma 1, and here will in the output at the 0th index will add 2 here, but which is wrong. Yeah, because the actual answer should be 4. So yeah, this is just totally wrong. So how can I think of using a Fenwick tree here? Hmm, given what are the observations needed to use a Fenwick tree here? You have an integer array. Cool. Return an integer array counts where counts of I is the number of smaller elements to the right of nums of I. So we have a range here as well. So we have a range, we have to perform this operation where we have to count number of smaller elements to the right of nums of I. But how do I think of Fenwick tree? We have nums.length, which is 10 power 5. So of course, our n square solution won't work. It will give us a clearly count of range sum. So it is right mode, so I put on Hmm. Oh, yeah. I was expecting a stack. Uh, oh, I saw the question. Was just where each numbers with its index and sort. What? How? This is just not possible. Universal count. Wait. Someone's at the door. Hmm. Count of range sums. How many numbers are smaller than the current number? How many numbers are smaller than the correct number?
Same way for one, count of small element to the right of one is no one. So answer is 0. So you can see that you can simply solve and you want to figure this out. Now, first very brute force, basic ways. Okay, I'll do one thing. I am at this index. I'll go. I know, okay, it is my ith value. I know nums of I what is x. I'll go on from I plus 1 up till the end, which is the count of I. And then the same way, if I am at the next index I every index log n. Okay, O of n is a very good case, but yeah. Next thing, okay, O of n is not working. So next thing is log n. O of n log n. Okay, O of n is a very good case, but yeah. Next thing, okay, O of n is not working. So next thing is
Writing. No.
you can think of it O of n square. So O of n log n. Now O of n log n for sure. As soon as we hear O of n log n factor usually comes by three things. Either it's a Fenwick or a segmentary like question, or it's a simple sorting, which we can do. Maybe it's a greedy kind of problem, or it is binary search.
Behind every breakthrough is a builder. This year at GetCon, we're celebrating you, the developers.
So you can also interpret this as the same way. So it is more or less either you're applying a Fenwick or a segmentary or a binary search or a sorting. Now, for sure, if you had watched the video of Fenwick tree, again, if you have not watched it, please go and watch this video. It is a complete explanation of a Fenwick tree with the proof of everything in very detail. So now, if you have watched this, so you remember a Fenwick tree, usually in a broad level, I can see it helps us in finding the range sum, in log n time. But again, I don't want to find the range sum. I want to find the count of small elements. That's not a range sum. Bro, that's an issue. We have to convert the problem. We know that this is the problem. We know this is the answer. So we have to convert the problem that, okay, I have to figure out the number of elements to the right. Now, I want to figure out number of elements. Okay, if this is the element, number of elements to the right of him, which are smaller than my cut element 5. So can't I do one thing? What if I would have gone in the increasing order itself, which means firstly I would have operative 1, which means, okay, I will encounter the small element 1, then I will go and check the right sum. Again, I can easily find the range sum in the right part. So as soon as I encounter 1, I'll put a 1 value. Okay, 1, I encounter once. 2 encounter, I encounter 1. Now you will see, I can simply go and find the range sum in the right part. Oh, maybe, which means that it gives the height. I encounter 1. Now you will see, I can simply
दरवाजा पे हाथ करने की.
go and find the range sum in the right part. Oh, maybe, which means that it gives the height. Okay, next big element is 5. As soon as I put a 5, like, okay, I encounter 5. I'll do a range sum in the right part of 5. Means that I encounter 1. Now you will see, I can simply go and find the range sum in the right part. Oh, maybe, which right sum. Again, I can easily find the range sum in the right part. So as soon as I encounter 1, I'll put a 1 value. Okay, 1, I encounter once. 2 encounter, I encounter 1.
Hmm.
Now you will see, I can simply go and find the range sum in the right part. Oh, maybe, which means that it gives the height. Okay, next big element is 5. As soon as I put a 5, like, okay, I encounter 5. I'll do a range sum in the right part of 5. Oh, so the problem itself can help us say that, okay, what I can do, I want to find the count of smaller elements. So rather than saying count of smaller elements, I will go in the order of smaller elements itself. Firstly, I'll go on to the smallest, then bigger, then bigger, then bigger. Then I know, okay, if I'm going on in the order of the element, then from smaller to larger, I know, okay, if I'm going on in the order of the elements from smaller to larger, I can simply say that, okay, bro, I know that this is a smaller element which for sure I'm going in the order. So if I want a small element to the right, so I know one thing, that I have been going in the order itself. So all the elements to the right which have 1 marked, which means they are smaller than me, and I want the count only, so I can simply do a range sum of this portion, and I know the range sum because of Fenwick tree or a segment tree is just overflowing. Although I don't much prefer segment tree over a Fenwick tree because a Fenwick tree code is very small. It is like a DSU code. There is segment tree over a Fenwick tree because a Fenwick tree code is very small. It is like a DSU code. How big the DSU code is, that big is our Fenwick tree code. So it is easily writable in an interview. But a segment tree code, it is not writable. That's the reason I usually prefer a Fenwick tree. But now we have got the intuition that, okay, bro, I'll do the exact same stuff. That I have this nums. I know in my Fenwick tree, I make a bit binary index tree array. But okay, remember one thing from the video, that always your BIT array is one big indexing. That is one thing I stress a lot. That make sure that you don't confuse in the values of it, because usually you do I and minus and all that stuff in your Fenwick tree. So be consistent that your bit is always one base. Now we know that we have the idea of how things work. We'll simply keep on populating, but we'll simply make sure that I populate one base. Now I said one thing, I'll populate and go in the order of smaller to larger. So I will firstly grab these elements. I will simply sort these elements. Now all these elements are sorted. 1, 2, 3, 1, 2, 5, and 6. But make sure, if I have sorted it, I also need to keep track of the original index. R and Y is index in it, because bro, at that index only you have to populate that. Okay, I found one because 1 is at index 3. For me, significance of index is very important, because for 5, here he is at index 0. For him, the right indexes are 1, 2, 3, and so on and so forth. For 2, its index is 1. So for him, the right indexes are 2, 3. So for me, values are also important and the corresponding indexes are also important. So I will keep a pair of value and index and then sort my values. Now I have got this specific sorted vector of pairs in which I have value and the corresponding index also. Now I will just go on in my bit. How I do it? Simple. I know that this is the first element counter. I know its index is 3, but my bit is 1 based. So I will increase the index. I'll make it a 1 based indexing. So 3 will become a 4 index now.
This is the bit vector. This is the okay. This is just counting the frequencies, not the frequency. Value and the index pair. Then sort.
Is saying as 4. I know, okay, having counted one element. Again, for me, element value is not important. I want the count of values, and for me, count is nothing but range sum. I'll have to say range sum. So for every element, I will say, okay, bro, I have got one element here. So I'll just say count is 1.
Think of Kafka.
Is nothing but range sum. I'll have to say range sum. So for every element, I will say, okay, bro, I have got one element here. So I'll just say count is 1. I'll say count is 1. Okay, one element I have got. What will happen? Okay, one element I have got and its count is 1, and that's it. So in your bit form, in your actual bit code, which means Fenwick tree code, you will simply say update value as 1 at this specific index, which is existing index, which is ID plus 1, because I know my bit array is 1 based. So you will see exact same stuff. That firstly, in the code itself, you will simply have a bit array, which you usually make for a Fenwick tree. Then you will make a pair. This pair you are making because you know that you have to sort this pair on the basis of its value. So first is value and next is its index, and then I'll simply sort it, and then I will actually apply this for every element. I'll go on to every element from left to right, which means from smaller to large element. I'll keep on going and keep on updating my bit. And let's say the next element comes in. Let's say 2 comes in. Its index is 1. I'll update at location 2. I'll say, bro, count has increased to 1. So I did the update operation. Update the value 1 because I just want to count it. That's it. Add the index, existing index, which is ID plus 1. Okay, update it. But bro, you are just updating. Where is the answer? You have to find the count, right? And you told me that count is the number of elements to the right. And I know I have been going in the increasing order. So whatsoever count, if I go and find right now, and keep updating my bit, and let's say the next element comes in. Let's say 2 comes in. Its index is 1. I will update at location 2. I will say, bro, count has increased to 1. So I did a update operation.
Okay. At that index, how many was that less?
Update the value 1 because I just want the count. That's it. Add the index, existing index, which is ID plus 1. Okay, update it. But bro, you are just updating. Where is the answer? You have to find the count, right? And you told me that count is the number of elements to the right. And I know I have been going in the increasing order. So whatsoever count, if I go and find right now, the sum of count in the right side of this specific thing, then I will easily find out how many elements were smaller than me in the right side. I'll go and simply say, bro, give me the range sum from index 3 up till the super end. So he will give me, which means your binary index tree or your Fenwick tree will give you a range sum from index I plus 1 to index n. How you do it? Simply, if you have not remembered how you do it, please go and watch the Fenwick tree video. Simply, we query n, which will give me the range sum from 1 to n, and then we query with ID plus 1, which will give me a range sum from 1 to ID plus 1. And that's how I can simply go and find out, bro, what is the range sum from ID plus 1 to n. And that's how I can simply go and find my answer. So this will be your answer of ID. Again, if you don't understand this, please go and watch the Fenwick video. But again, if you are looking for an interview perspective, please go and look for the next part of this in which we will solve it by another algorithm. Now, for sure, we will just finish it up. Look for the next part of this in which we will solve it by another algorithm. Now, for sure, we will just finish it up, wrap it up. That we have 5. Then we will go at the index ID plus 1. We at index 1, just put a count of 1. Okay, because we just want to count. We just find the range sum. For him, the range sum is 2. And that's how you are actually populating your answer itself, which means answer of index 0 is populated with the range sum from ID plus 1 to the end. And let's say last one is 6. Update the index 3, find the range sum, which is 1, and then update the answer of 2 as 1. And that's how you can simply get the answer. So the code is exactly pretty simple. That this is the just small Fenwick tree code. This is the just small Fenwick tree code. If I just go back and show you, this is the only part of the and that's the reason. That's a beautiful part. Code is so short. Again, the entire code I've explained in this video, we will just use as a boilerplate code. Now, as we saw that we will simply make a bit array for our Fenwick tree. Then we will simply push back elements and indexes, and then we will sort it. Now, I'll go on to every element in the increasing order. So I'll just simply iterate all the elements. And then firstly, as soon as I encounter an element, please update value 1 at this index ID, which I am also. Okay, range sum from ID plus 1 to the super n, which is n. And that's how ultimately I will be populating my answer itself, and that's going to be your answer. Now, this is O of n log n because of using of Fenwick tree, and space is O of n because of the bit array which you are making. Now, the code and all that thing you can find here itself. But now, this is the easy approach. But it's highly chance, like that's a highly possible that your interviewer might not even know about a Fenwick tree. And usually in companies, people are very just basic DSA persons, so they might not know Fenwick tree. In that case, there is nothing. As you saw in the very beginning, I told you it's a log n factor, right? So I can either use a Fenwick tree or a segment tree or a merge sort or maybe a sorting. Now, sorry, I can use a sorting or I can use a binary search. Now, for sure, when I told the term sorting, why not? Why not the algorithm of a sorting, which is merge sort? Now, simple. I use a normal basic merge sort. Aryan, but tell me, how you even got the intuition that you will not use a binary search but a sorting? Because if you remember, binary search I can use only when the things are sorted. But merge sort is I can try to sort stuff out. I will try to sort, which means while sorting the stuff, maybe I can find my answer. So that is what I will try off doing. So I'll apply a simple merge sort. If you don't know a simple merge sort, it just simply says that you have an array, keep on dividing the array into chunks, and then merge that chunk. And how's that useful? You will see that part. But yeah, that is a basic merge sort, which means divide it and then keep on merging it. That's the basic idea of merge sort. Simply how you divide it as you do a simple division in a binary search. That you have your left, you have your right. Now you need to divide it in half. So you need to do a mid. Mid will be again simple. You can do a left plus right by 2, but a good practice is to do left plus right minus left by 2. That you have also seen in binary search. Now, when you have seen that, okay, you can do a simple division. Ultimately, remember what's the aim of merge sort? As the thing says, it's a merge sort. It is a sorting algorithm. So it will try to sort your answer. It can be either increasing or decreasing depending upon what you want. But remember what we want. We want it in decreasing. And why are you saying decreasing? Because if you remember, we want the count of small elements to the right. So we want smaller elements to the right of our value. So we want, again, merge sort can sort in both increasing and decreasing. But now my aim, my responsibility, or my requirement is that I will sort it in the decreasing order because I want the count of small elements to
We are looking for 150. 5 most people.
So you just
Hey everybody, this is Larry. This is day 23 of the LeetCode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. Count of smaller numbers after self. Okay, so which one is this? You're given a nums array and you're returning a new count where it counts as the number of smaller elements to the right of nums of I. Okay. I think there are probably a lot of ways to do this. I'm trying to think whether... So there at least one obvious way of doing it, which is just like a binary search tree type distributed thing, and of course that'll be n log n. Can we do it in linear? And n log n will be fast enough for competitive for most n's, so that would have been good enough especially if I was in a contest. But for this one, let's see, can I do smaller 6 1 6 2 2 2 regular 5? No, I think like I was just trying to think whether I can, is there a sort of like a mono in this case, probably mono stack, but I don't think so. I think you need the differentiation for every one. So yeah, so that's that. So I think this is just using, in this case, a library, but you can also think about, there are a couple ways you can do it, right? What are the numbers 10 to the 4th, and maybe negative, but that's okay. You can actually, so there are a couple things you can do. There's BIT, which is binary index tree, or Fenwick tree. There's also just seg trees in general, which is segment tree. I think either of which is probably a little tough if you haven't already done it. There's also BBST, right, like binary or balanced binary search tree. And then the thing that I'm going to use is, yeah, and there's also like stuff like I forget what it's called, like the stuff like, skip list, order statistic trees, etc. Right? There are a lot of stuff like that. It depends on your language and your library and what you can do. The way that I'm gonna do it is today probably a little bit lazy, but so from in Python anyway, there's this thing called sorted list, and it is kind of it is kind of what it sounds like, which is that it's just a list that is maintained to be sorted. There's some caveat about the actual complexity and the time stuff like that, but for the most part, it should be okay. So yeah, so let's do that. Yeah, I'm not. This is it that much with respect to secretary and bit. Yeah, I'm not gonna go over it that much with respect to secretary and binary index tree. Definitely, if that's what you're interested in, look it up, do some research on the Googles or the YouTubes or whatever. This is in the case that you are wanting to learn those things. This is a very basic implementation, or like this is a very basic request of those things. So definitely look those things up. If that's what you want to learn, if you have a couple of hours or a couple of days, if you will, to want to learn, this is a good application of like just plugging it in and trying for it. Okay. So then now we have a sorted list. As you go to sorted list for x in nums, and we want it kind of backwards, of course. Let's do a binary search, right? We want to, so we want.
Okay. 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 So let's open now.
Hey everybody, this is Larry. This is day 26 of the June LeetCode Daily Challenge. Let's get to it. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about.
Was included for what's that? Every circle doesn't keep it as well. Oh,
315, count of smaller numbers after self. You're given an integer array nums, you have to return new. Today's problem, count of smaller numbers after self. So you're given an integer nums, you have to return a new count array. The count array where numbers of I is the number of smaller elements to the right of nums of I. Okay. So there are a couple of canonical solutions to this. It's a studied problem-ish, at least in competitive. I think for example, the segment trees, there's binary index trees, some things that I talked about earlier, because you can just literally as a query, you just think about your patterns, right? You go from right to left, you go, okay, 1, what's more than 0? Oh, sorry, what's 0 or smaller? None, 0, and then 6, you do what's 5 or smaller, and so forth. Get the count. That's how, and then it would ask you about it, and unless you have a very good understanding of it, good if you bring up on an index tree, should be on high powered. I don't want to mean to scare you. Binary index tree, 0 to 1, 0 to 4, and so forth. So that's how from that you can change that into a query from that instance, because you can just get the count of numbers from 0 to 0, 0 to 5, 0 to 1, 0 to 4, and so forth. So that's how the general idea behind binary index trees, 0 to 1, 0 to 4, and so forth. So that's how the general idea behind binary index trees and segment tree. But that's of course too high powered. I don't want to mean to scare y'all. I personally don't think segment trees or binary index trees should be on any interviews. So, and I don't even know if it's good if you bring it up on an interview, because then they would ask you about it, and unless you have a very good understanding of it, it just becomes a buzzword, and then they kind of discounted you a little bit. I made that mistake before, not gonna lie, where I'm like, oh yeah, I think this has a solution that uses XXX algorithm, and then they asked about it. I'm like, oh, I guess I wasn't as studied about that algorithm as I thought I would. So then they just think I was BSing. But anyway, and it happens because when you do a lot of problems, there are a lot of situations. But I think a fundamentally easier thing as well, which is to keep a binary, depending on your languages, you could keep a binary tree, and then just as we said before, you just kind of keep inserting and then just search on that binary tree for numbers that are smaller than it. That seems pretty straightforward. In Python, there's a thing called sorted list, and that's what I'm going to use, which has the same idea. You can keep on binary search on it, which is why.
where is the solution using Fenwick tree?
Smaller numbers after self. You're given an integer array nums, you have to return new count array. The count array has the property where it counts up.
Great.